Ronak, welcome to the webinar. And maybe if you could introduce yourself a little.
Thank you, Paul. Yeah, I'm Ronak Samani. I'm a technical engineer at Maxon UK and Ireland. I've been working at Maxon as a technical engineer now for 5 years. Before that, I was studying aerospace and aeronautical engineering at the University of Leeds, where I graduated with my bachelor's and master's. And yeah, now for the past sort of 5 years, I've been supporting the selection of drive system components for Maxon and providing technical expertise about our products.
Oh, thank you very much. Fellow Leeds graduate here. So moving on, perhaps maybe we could talk a little bit about the overall topic of today's presentation, which is obviously motion control. Maybe you could talk a little bit about Maxon's role in this area.
Yeah, thanks, Paul. Firstly, on the aspect of motion control systems, if you look at any motion control system, Paul, it has the basic task to control the movement of the load. But for Maxon, it's more than just movement. It's about enabling precision and reliability into that movement, especially in applications where performance really matters. All of a sudden, what you have, Paul, is a shift in focus to ensure that the motion is optimized for the specific needs of that application. And that focus is reflected in the design of our drive system products as well. If I just show you a little overview of our products. So here you have the entire range of our DC brush motors. Again, the design of that focus in our brush motors, our ironless windings, our brushless motors, which are also ironless windings, the iron cord windings. It's reflected in the design of our gear heads. We have various gear head options available with different design adaptations, call that standard metal gears, ceramic gears, high power variants, ultra performance, low noise, low backlash. They're just to cite a few, but also in our encoders, our optical encoders, magnetic, inductive, and well, a component that's today's topic is controllers. And controllers, Paul, they're the central part of a motion control system. That's where all aspects of motion and the entire application comes to meet together. So it's really important that controllers have the ability to be versatile, that they're flexible, and that they're modular. And Maxon achieves that by offering sort of an extensive range of hardware platforms. You have sort of here a module electrical design that's designed to be incorporated into a custom specific motherboard. We then have sort of compact variants, which are modules and compact boards together, still to keep that compactness in the integration of the assembly and keep the cabling to a minimal, and something a little bit more robust, which is these encased housing versions. We have a multi-axis one here as well. And within these hardware platforms, you'll find variants of power amplifiers to perhaps suit a single axis or multiple axes in an entire drive system. Again, just to sort of attain to different power requirements that a certain specific axes might have. Depending on sort of hardwares as well, it might support DC brush motors or DC brush motors or both. And that's really important for brushless motors because it's the responsibility of the controller to conduct the commutation of the motor. Different sort of, again, hardware platforms have to support various sensor types, also encoder protocols. It's, again, the responsibility of the controller to execute control algorithms and correct for any deviances, and also to maintain the limits of the system, whether that's electrical, mechanical, or even thermal, so that the motion control system, the application, can perform what it was intended to do. So that's just a few examples of maxon's role in motion control systems.
Okay, so perhaps moving on from theory to practice, maybe you could give us an idea of how motion control technologies are used in real world applications and what makes them so critical to system performance.
Oh, yeah, there's so many applications that you'll find the technologies used in, Paul, across various markets. You'll see sort of within medical industry, probably used in surgical systems, active implants, in industrial automation, for sort of intelligent locomotion systems, AGVs, industrial power tools, aerospace in propulsion, driving sort of unmanned aerial vehicles, actuation devices, and even sort of going to robotics. And why they're so critical to system performance is actually governed within the markets that those applications operate in. Each market sort of imposes its own demands, whether that's from quality assurances, regulatory compliance, safety standards. Essentially, motion control systems must be designed to meet those expectations that the markets set out. And therefore, sort of from a system performance point, it generally becomes a question on sort of application level behind precision, accuracy, and repeatability expectations. When it comes down to how they are used, trying to be a bit sort of generic across the entire range of applications, Paul, it's really two-part. And firstly, it'll be down to sort of the control method that the system is designed around. Again, concerning those parameters that I mentioned for precision, repeatability, and accuracy. One of the methods that applications might adopt is open loop control. And with open loop control, usually these types of applications are inherently stable. In other words, the response of the system is known. And if there are any sort of interferences or varying boundary conditions, that won't affect the response of the system. So what you'll find is that in sort of a system architecture level, there's many drives out there that could be set up in open loop control modes, but they're more simplistic and there's less sort of components that's needed because the output variable doesn't have to be monitored. Another method that applications might sort of be designed around are closed loop methods, and that's quite common. And that increases sort of the precision and the accuracy because the distinct feature being that the output becomes monitored. And with sort of the output variable monitored, you close the loop with extra sort of sensors, and that tends to increase the accuracy of the system. The sort of second part to it is down to control tasks, and they serve as the input variables to those control methods that I spoke to. And that might be torque control, speed control, position control that you might see for a given application. Actually, it's always a question of torque control. At the end of the day, masses have to be set into motion. There's accelerations, there's decelerations. The motion might have to lift, lower, or even just hold something in tension. So what you'll find in modern motor controllers is that the central to their loops in control are current controllers. And that's because current and torque share a linear relationship when it comes down to DC brush motors and brushless motors.
Perhaps it might be useful if for anybody who's not completely clear, if we could outline the differences between motors and motion controllers.
Yeah, that's great, Paul. So what I have here is a motion control system, and that's comprised of a motion controller and a motor controller. And the motion controller essentially, the way that you want to think about this is in a hierarchical form. So the motion controller serves as the upper level commanding component, and the motor controller serves as a lower level component within a motion control system. And the key fundamental difference is that this motion controller is a programmable controller. It contains the application program, and its purpose is to coordinate and command tasks to the motor controllers. The motor controllers, what you'll find, tend not to be programmable, but they have firmware that allows for configurability, and the purpose of it is to execute tasks from the motion controller and then regulate power to the drive. And for the entire motion control system to function, there needs to be a communication link. And what you'll see in sort of terms of setup, and again, that sort of influences the definition between the two. The operating mode is a consideration that will dictate the architecture as well between motion controller and motor controller. So here is sort of an example of a closed loop system. So that's one of the control methods that I just mentioned. And that's one of a position controller. And in this case, the motor controller is configured to operate in a mode of operation called profile based, which is point to point operating mode. So essentially, the motion controller will just set the motion parameters, and then they'll command the motor controller. And it's then the responsibility of the motor controller to process any motion profiling or trajectory generation. And that's based on a specific motion profile for sort of maxon, that's motor controllers, positioning controllers, that's based on a trapezoidal profile. And then it's the motor controller that has the responsibility to calculate any of the intermediate values based on the configuration and sort of compute the data exchange for communication. So it's not really used for applications that are in real time. Another architecture sort of difference. So here again, we have the same closed loop system control method with position task. Again, you can see that the feedback is closed with a sensor, but the controller here is configured to operate in a different mode, which is known as a cyclic operation mode. And now that tends towards applications that are real time. And the difference between those two modes, and actually even down to the setup for motor controller and motion control architecture, is where the trajectory generation is. And that actually shifts responsibility to the master. So that's responsible now for any motion profiling that is then processed by the motion controller. And then the motion controller would transmit updated sort of set values to the control loops, and the amplifier is still powered there. And that sort of changes as well the data exchange requirements. Usually tends towards real-time capability, especially for multiple axes, and you see something like CAN open being used rather than USB RS-232, the sort of base standard that you'll find in hardware. And then finally, you have, again, an example here of a sort of very strongly coupled application, and more responsibility now is given to this motion controller. So you can see it's not just motion profiling, but it's also processing the control loops. And the motion controller perhaps might be sort of executing this for several axes, but for the motor controller, it's just configured as essentially a current controller. It's used in a cyclic torque mode, and it's just serving as a power amplifier. And again, this is a sort of real-time master motion system with real-time communication. So just to sort of summarize it all and put it in a nutshell to understand the fundamental differences, it's how they operate together, how the application axes as well coordinates with each other. So the stronger, the faster, the more coordination and synchronization there is in an application or in an architecture, more of that responsibility shifts to the motion controller. And the less that the axes become coordinated, the more the responsibility can be done on the motor controller aspect.
Okay, thank you. Moving on perhaps to what factors people need to take into account when they're choosing a controller.
Yeah, and that really requires a holistic approach, Paul. So I've got here just an overview of sort of the selection process for a drive system, but also what needs to be taken into account when it comes down to just setup of motor controllers and motion controllers and how you might want to take the architecture. But initially, what I can sort of advise to anybody is to really conduct a thorough situational overview of the application. I mean, that's the most crucial part of the selection process. There's sort of four main areas to really question, I would say, to any sort of design engineers out there. Really begin to define the mechanical layout. So the intended motion, what the mechanical configuration is. From that, you can sort of get a good outline of the boundary conditions, understand the spatial envelopes, any sort of compliance factors, environmental conditions that need to be met, service life requirements. You can get an understanding quite quickly with the control task for the application and sort of arrive at a preliminary solution at a motor control or even a motion control level. Verification of sort of power. Again, power supply is a big factor to take into account and ensure that there's sufficient power available to achieve the operating points of the entire system and sort of compensate for any losses, and also regulate the right power to the controller and any peripherals around it. And yeah, I think that's the sort of the main point, is to conduct an entire situation overview, to analyze the problem and ask yourself, sort of, do I have all the necessary information available to perform the right selection and in turn complement the setup for the drive? And what people tend to sort of find is what sort of starts off something as like a theoretical feasibility study becomes an iterative approach for selection. So once you have a drive system that's clearly described as a whole in its environment, where boundary conditions become a lot more clearer and any sort of restrictions are highlighted, it's a lot more easier to optimize the selection and avoid any sort of dead ends. So based on sort of this step-by-step basis, in reality, you'll probably apply sort of steps 3 to 7 several times. It really is an iterative process. But the more that can be defined from the beginning, you can arrive at an optimum solution sooner.
Okay. And finally, big question. What do you see as the future of motion control?
Yeah, I wish I had a crystal ball, Paul. But no, I think what's sort of seen at the moment, market trend is a lot around artificial intelligence, and perhaps what might be the case in motion control is the controllers will start to adopt modules where AI perhaps starts to take care of some predictive maintenance, predicting failures earlier. I'd envision to sort of see algorithms become a lot more sophisticated, whether that's from a tuning basis, so becoming a bit more adaptive, again, suiting to a wide range of varying boundary conditions. Faster processing, smaller components. That's sort of where I see the shift to be.
Okay, thanks, Sarah. We do have some additional questions here, and maybe I could put them to you. Here's one. How are advances in multi-axis control reshaping automation and robotics design?
Again, I think it sort of goes back onto that sort of final point with the future of motion control. We'll start to see smarter algorithms incorporated into them. Maxon just recently as well. We have two sort of robotic drive systems that have hit the portfolio that have sort of adaptive algorithms already built in. A new speed controller as well that Maxon released had a sort of feature known as field orientated control, but just based on Hall sensor feedback. So I'd see that from an advancements point, it's sort of down to control algorithms, which is quite important for robotic designs, but also to keep things compact. I mean, space is such a big factor in robotic applications, whether that's exoskeletons or joints, or you see those sort of robotic dogs out there. It's all about sort of getting that high power density in a compact space.
Okay. And we've touched on selection of motion controllers. So, but what are the most common mistakes engineers make when selecting motion controllers?
I guess over sort of the past 5 years, it really comes down to formulation of drive requirements. But again, like I said, it's such an iterative process. I mean, with sort of applications out there, there's several design teams that are communicating together. But again, the clearer that those drive requirements can be formulated, the easier that it becomes in terms of selection of components and even setup of controllers. And again, just keeping in mind controllers out there on the market, industrial sort of motor controllers, you'll see in terms of hardware, they're either speed controllers or they're position controllers. And that in itself simplifies the architecture. But it's just good to keep in mind to the interfaces that these controllers are capable on, especially as well when it comes down to encoder protocols. It can be a bit of a bite in selection.
The inevitable AI question here is, how is AI or machine learning influencing the future of motion control systems?
Again, just sort of that predictive maintenance side, sort of predicting failures earlier, optimizing trajectory generation and motion profiling. I think the more that sort of machine learning gets implemented, the more it tends to learn about algorithms, the sort of smarter that they become, and the more energy efficient that they can be in use.
Okay. Finally, what skills or knowledge should new engineers focus on in motion control design?
It's a tough one to answer just because of sort of how broad of a discipline sort of engineering is now. I mean, myself, obviously, 5 years sort of in the industry, but if I could go back in time knowing that I would be at Maxon, I'd probably sort of poke myself down the avenue on sort of mechatronics, embedded systems, sort of real-time programming. That's definitely an avenue to explore for engineers focusing on motion control design.
Okay. Unfortunately, that's all we've got time for today. But if there are any questions that the audience has asked that we haven't had time for, we will pass those on to Maxon and they will answer them for you offline. Equally, we would encourage you to get in touch with Maxon directly. But in the meantime, it just remains for me to say thank you very much to Ronak for joining us today, and to thank you all for joining us as well. Thank you very much.
Thank you.